Alright guys, so we are going to start looking a little bit further at matter with the different types of matter and determining whether matter is a solid, liquid, or gas is going to depend on what forces are within that matter. So I want to explore that a little bit more. So we do have the kinetic molecular theory of gases. We talked about kinetic molecular theory in Chem 1, that particles in any substance are in constant motion, even in solids. But we're going to deal a lot with gases this unit whenever we get later into gas laws. But looking at the molecular theory of gases. So gases are composed of small, hard spheres of insignificant volume. So these particles are so tiny, there's lots of empty space, so they do not have a lot of volume. With gases, there's going to be no force of attraction or repulsion between particles. So we're going to talk about intermolecular forces in a little bit. Those do not exist in gases. We're only going to deal with those in solids and liquids. And part of it is because the particles are moving very quickly and they tend to be so far apart. So the particles in a gas are in continuous, rapid, random, straight line motion. So this has a little bit of physics worked in, where particles will move in a straight line unless acted on by another force. So the particles will move until they hit something and bounce off in another direction. But each particle is moving independently. They are not all moving the same direction. So they're not all moving like towards the right or up. Every particle is going in a different direction until it hits something and goes a different direction. One thing that we'll talk about a little bit more later whenever we start looking at reactions is we talk about collisions. But collisions between gas particles are what we refer to as elastic. That means that energy can be transferred whenever those particles do collide, and the energy can be transferred from one particle to the other, and then they go off in another direction. But energy is not lost overall. It just goes from one particle to the next. And then all of these theories with gases describe ideal behavior of most gases at high temperatures and low pressures. We're going to talk about later this unit of when things do not behave as expected, or they do not behave ideally, but that's going to come up later this unit. Let's look at our states of matter. We have gases. We said there's lots of empty space between gases, so they do have a very low density because there's not as many particles trapped within that amount of volume. The density is going to be affected by temperature. So if you cool it down, those particles slow down. They tend to get closer together. With gases, because there's empty space, they also have a very high compressibility. We can push down on gas particles and force them to fill that empty space. And then with gases, the particles spread out to fill the container. So if we take 2 liters of gas and pump it in a 5-liter container, the particles will spread out to fill that 5-liter container. With solids, remember those particles are tightly packed together, so it has a greater density. Density is not affected by temperature because that solid cannot expand or contract. It can't be compressed at all. So like I said, they are incompressible. There's not empty space between the particles that you can force those particles into. And with solids, they're completely rigid, so they have a set shape and volume. So the shape and volume of solids do not change. Liquids are going to be kind of an in-between for us. They're more dense than gases, but less dense than solids typically. They're virtually incompressible. So you cannot take um, like a container of water, push down into it and it not overflow. The water will kind of move out of the way and fill in more space. So you can't actually make the particles go closer together. And with liquids, they take the shape of their container. So if it's in a can, it will have that cylindrical shape. If you spill it in the floor, it will have a shape of a puddle. But these do have a definite volume. So like if I have a can of soda that is 12 ounces, if I pour it in a cup, it is still 12 ounces. The shape can change, but the volume stays the same. Looking at these particle-wise, in solids and liquids, those particles are close together. Remember, solids, they're kind of tightly packed together. There's a very nice orderly pattern. Liquids are a little bit more random, but the particles are still touching. Whereas in gases, those particles are going to be very far apart. So you have lots of empty space between those individual particles. And a lot of times, the state of matter is going to depend on what attractions there are between particles. So let's start looking at interparticle attractions or intermolecular forces. You'll kind of hear both terms used equally. But these are attractions or forces that hold one particle to another in a solid or liquid. So this is the attraction between different molecules holding them together. And like we said, this is only in a solid or liquid because gases do not have attractions between particles. So here you can see these would be like water molecules being attracted to one another. This is going to be like a protein structure where they're attracted to one another. And in a solid, remember those particles are locked in place due to strong attraction between particles. So there are different attractions that hold one particle to another in a sample. We've already talked about ionic bonding and covalent bonding. So remember, ionic bonding, the ions transfer electrons and they have an attraction to one another. Covalent bonding, they're sharing electrons, but we're going to look at those intermolecular forces. And the intermolecular forces are only going to show up whenever it's in one of our condensed states, so the liquid or solid. Ionic bonding, we tend to not be able to reach high enough temperatures to have things that are ionic as gases. But covalent bonding still exists even as something is a gas. So within the molecule, you can have covalent bonding, but you will not have those interparticle attractions or intermolecular forces between two different particles. So with the interparticle attractions, the type and strength of attraction is going to affect the physical properties of a substance. So for example, the stronger the interparticle attractions, we're going to have higher melting points, higher boiling points, and also a higher viscosity. It's going to resist flowing and moving typically. So the particles will want to stick together more. So like I said, interparticle attractions or intermolecular forces you'll hear a lot more often. Intermolecular forces, so intermolecular refers to the forces between two different molecules, so not within one molecule. So it would be one water molecule attracted to another water molecule. If it is within one molecule, inside a molecule, those are referred to as intramolecular forces. These are like our covalent bonds or our ionic bonds. And molecular means that it's not present in ionic compounds or metals. So that's where we may look at interparticle forces versus intermolecular. So intermolecular is between molecules that are going to be those covalently bonded ones. So some things to note: intermolecular forces, because they're between two different molecules, are weaker than intramolecular forces. So these are going to be weaker than ionic bonds, weaker than metallic bonds, weaker than covalent bonds. And for example, like, it's easier to vaporize water than to actually break apart the covalent bond to separate into hydrogen and oxygen. We can boil water to make steam, but it's going to take electricity and a lot of energy to actually sever that bond to make hydrogens and oxygens versus water vapor. So some things to note: during phase changes, like when we are melting, freezing, boiling, the molecules are still intact. If you have ice and you melt it, it went from solid water particles to liquid water particles, but it's still water particles. Whenever you boil those, they are now gaseous water particles. So you didn't actually break the covalent bond whenever you're going through a phase change. So the energy required to actually change states is used to separate molecules from one another. So that means that it has to overcome or weaken those interparticle attractions or intermolecular forces. So whenever we are melting from ice to water, we are weakening those intermolecular forces that are holding the water molecules together. Whenever we are boiling, we are actually like breaking apart that attraction between the water molecules. So there are three main types of intermolecular forces we come across, and these are ones that we looked at in Chem 1, but we're going to dive a little bit deeper in these. So we have dipole-dipole forces. You'll also hear these referred to as dipole interactions. We also have hydrogen bonding. This you heard in biology and Chem 1. And then we have London dispersion forces. There are also a couple where we are going to mix some of the forces. These are going to be new ones for you that we did not talk about in Chem 1. So we also have ion dipole forces and dipole-induced dipole forces. And we're going to talk about each one of these and when you would see these, what type of substances would have these. So looking at those dipole-dipole forces, here, remember, a dipole is a substance that has two poles, so a positive end and a negative end. So with dipole forces, the positive and negative ends of polar molecules will interact with one another, resulting in a net force of attraction. So the positive end of one molecule can be attracted to the negative end of another molecule. This is about 1% as strong as covalent bonds, so it is weaker than covalent bonds. And this becomes weaker with a greater distance. The further apart those particles are, the weaker that dipole attraction is going to be. So looking at this, we have two polar molecules. The positive end of one is attracted to the negative end of another. But you can actually have a bunch of molecules that are attracted to one another. So here you notice that the negative end of one molecule is attracted to the positive end of all neighboring molecules. So the attractions you can see in red, they can also repel one another. So those are the yellow dotted lines, or those repulsions. This is where particles are going to be held in a certain alignment overall. We also have hydrogen bonding, and like I said, this you talked about in biology with like DNA and proteins, and then we talked about it in Chem 1. But hydrogen bonding can be thought of as a very, very strong dipole force, and this is only going to occur between molecules that contain hydrogen attached to a fluorine, oxygen, or nitrogen. So you can remember that hydrogen is fun, F-O-N. That's whenever we tend to have hydrogen bonding. It's only these three elements because they have a very high electronegativities. So there tends to be a very large difference in electronegativities between hydrogen and these three. We also tend to have hydrogen bonding because these particles are very small, so the molecules can be closer together, resulting in a larger attraction. These, yet again, are still weaker than actual bonds. These are about 10% as strong as an actual covalent bond. A lot of times we said that the intermolecular forces can determine those physical properties of substances. If we look at this chart, this has different substances and it shows their boiling points. And you'll notice that the red line, the very peak, is that water molecule that is very electronegative. But then as soon as you get to those larger atoms like sulfur, that's going to be a little bit bigger, it doesn't have as high of a boiling point because there's less of an attraction between particles. Same thing with like the hydrogen fluoride. It's only an acid if it's aqueous. So if it's a gas, it's hydrogen fluoride. But the hydrogen chloride that is right below it has a lower boiling point because there's not as strong of an attraction. This is kind of the data that we use to determine which ones specifically have that hydrogen bonding occur. So this, like we said, happens whenever hydrogen is paired with fluorine, oxygen, or nitrogen. So whenever it's paired with oxygen, it does make water. And like we said, this can be thought of as a very strong dipole because oxygen is more electronegative, so it is attracting those electrons. So the oxygen ends up being slightly negative and the hydrogens end up being slightly positive. So what that results in is whenever we have a bunch of water molecules, the hydrogens are going to be attracted to that electron pair that is on oxygen. So you tend to see a lot of these align together overall. We also looked at hydrogen bonding in biology. The base pairs in your DNA are held together by hydrogen bonds. So you can see the double helix here. We're looking at this AT, this adenine thymine. That attraction, those dotted lines, are the hydrogen bonds that we're looking at. So you can kind of see these dashed lines between the two bases representing those hydrogen bonds. And remember, hydrogen is covalently bonded to one atom. So, and then it is hydrogen bonded to another. So if you're looking at the AT base pair, you have this hydrogen is attached to a nitrogen covalently, and then it is attracted to the oxygen on the other base pair. And they don't have to have hydrogen bond to nitrogen, oxygen, or fluorine on both molecules. It just tends to be attracted to one of those very electronegative elements on another molecule. This was also how like polymers and proteins are put together. So here you can kind of see the structure overall where we have that hydrogen paired to nitrogen. And in the larger structure, that's where that attraction occurs. Now we're going to move on to Lund dispersion forces. These tend to be the weaker force. Not always, but in general, this is the weakest force that we tend to come across. And nonpolar molecules and atoms can still exert forces on one another, even though they're not polar and not having that attraction. Or if they did not have some attraction between particles, they would never be in a liquid or a solid form. So we know there is some attraction between molecules. It's just a weaker attraction than those dipole or those hydrogen bonding. So if we take carbon dioxide, for instance, carbon dioxide in its solid state is dry ice. Carbon dioxide, if we were to sketch it out, if you remember, it has those two double bonds with oxygen. And there's no dots in the center atom. I'm not going to draw the extra dots. So that is nonpolar. If London dispersion forces did not exist, this could not exist as dry ice. Same thing about like iodine. That's I2. It's one of our diatomic ones. We know it's nonpolar because one iodine is not going to be stronger than the other. We do have solid iodine. That could not exist without these London dispersion forces. With London dispersion forces, the reason that they exist, what causes that force of attraction, is that electrons are not going to be evenly distributed at every instant in time within a molecule. So for a split second, the electrons moving in their electron cloud are going to be unevenly distributed, and that creates an instantaneous dipole. So for that split second, we're going to have part of the molecule that's slightly positive and part of the molecule that's slightly negative. And this induces a dipole in the atom next to it. So the electrons in one atom can influence the movement of electrons in the following atom. So to show you what this looks like, here we have two hydrogens that are nonpolar. Right now the electrons are equally distributed. But if one of the hydrogens, the electrons move more towards one side, and we end up with a slightly positive end and a slightly negative end, that causes the electrons in the neighboring hydrogen to shift as well, creating that dipole, that instantaneous dipole with the positive end and negative end. With these London dispersion forces, they are weak and they tend to be very short-lived. So like I said, for a split second, those electrons are unevenly distributed, but then they go back to normal because they're in constant motion. These forces tend to last longer at lower temperatures. So at lower temperatures, those forces last longer. That's why at lower temperatures, those substances can exist as solids. Eventually, these do last long enough to make liquids, and whenever they last even longer, they can make solids. But these tend to be much weaker than the dipole forces and the hydrogen bonding. There will, of course, be some exceptions, but these tend to be the weakest of the three. So with dispersion forces, their strength is based on polarizability of the molecule. This is a word that you will want to use if you're asked like why one has more dispersion forces than the other. It's going to be based off of polarizability. Polarizability is the measure of the extent to which the electron cloud of an atom or a molecule can be distorted by an external electrical charge. So in general, the more electrons something has, the more polarizable it is. Therefore, it will have stronger dispersion forces. So larger molecules that have more electrons are going to be more polarizable compared to others. So here we have a sample of pentane and a sample of neopentane. It just looks at the overall arrangement of it. With these, strength is based off of polarizability of the molecule. If we look at these, they have the same formula. So based off of electrons, we could not tell which one of these is more polarizable. However, we can also look at the overall shape of the molecule. to help determine which one would have stronger forces. So let's look at these a little bit more based off of their arrangement. So here we have that pentane, which is spread out, it's elongated. There are multiple atoms that can interact with one another. So there's a large area that they can interact. Whereas the neopentane that is more compressed, there's only a small portion for those to interact. So that would have weaker forces because there's going to be less interaction between the molecules. So let's look at an application of this. You could be asked which one has stronger dispersion forces, hydrogen or iodide. If we look at them, hydrogen, H2, is only going to have 2 total electrons, or even 2 total electrons. Iodine by itself has, I believe, 55 electrons. Sorry, I don't have periodic table right in front of me. So iodine has a larger electron cloud. There are more electrons there. Therefore, there are going to be more interactions between the electrons, meaning iodine has a higher London dispersion force, simply because there are more electrons, so it is more polarizable. So looking at our 3 primary intermolecular forces we looked at, we said the weakest was going to be those London dispersion forces. This occurs, we're going to talk about it majority of the time, between nonpolar sources. But London dispersion forces really exist between everything. But it is the primary force present in nonpolar substances. The strongest intermolecular force is that hydrogen bonding. And remember, hydrogen bonding only occurs whenever it's hydrogen attached to a fluorine, oxygen, or nitrogen. So remember, hydrogen is fun. That's how you can remember it. And then the one in between was the dispersion force, or not dispersion, excuse me, dipole forces. And remember, this occurs between polar molecules, where you have that positive end of one molecule attracted to the negative end of another. Looking at all of these forces, there are interactions that occur, and there's a couple of these we still have to talk about. But if we are dealing with ions, if there are only ions, it is an ionic compound, meaning that it only has ionic bonding. That's going to be the primary force there. We're also going to talk about if that ionic compound is interacting with water. We're going to look at that in a moment. If there's molecules, though, you have to determine if the molecule is polar or nonpolar. Nonpolar molecules tend to have the dispersion forces. If we have polar molecules, we can have dipole forces, but if it has the hydrogen with fluorine, oxygen, or nitrogen, that also has hydrogen bonding. And then we're going to look at what happens if a polar molecule is trying to interact with a nonpolar molecule, and that will be a dipole-induced dipole. So we're going to look at a couple of those special forces for a minute. So those ion dipole forces, we said occur when you have something ionic interacting with something polar, typically water. So here it shows aqueous sodium chloride. So it's ionic, but it would state that it is aqueous. What happens there, I apologize, I'm trying to write with my mouse. What happens there is whenever that ionic compound is in water, if you remember from Chem 1, we talked about net ionic equations where that ionic compound will split into ions. Here's the reason that it splits into ions whenever it's in water. The positively charged end of a polar molecule is attracted to the negative ion in the ionic compound. And then the positive end, or the negative end of the polar molecule, is attracted to the positive ion. So that attraction causes the ions to separate, and the water molecules will surround them with the positive ends attracted to the negative ion and the negative ends attracted to the positive ion. So anytime you have something that is ionic in aqueous form, it's going to be one of these ion dipole forces. And I don't have a drawing of the dipole or dipole-induced dipole, but it's where something like iodine that has a lot of electrons, those electrons can be attracted to the positive end of water. And that's what causes something like iodine to be in liquid form or in aqueous form where we can still dissolve it. Looking at our overall air molecular forces, our strongest that we've talked about so far is ionic bonding. Hydrogen bonding is going to be weaker than actual bonds. Below hydrogen bonding, we have those dipole-dipole forces. And then remember, our absolute weakest are those dispersion forces. We last unit mentioned metallic bonding. That tends to be weaker than ionic bonding. And here's where there's some discrepancy. There's a couple of things that occur. Covalent bonding is typically weaker than ionic bonding, but we're going to talk about some substances where there are a multitude of covalent bonds, causing it to be stronger than even an ionic substance. We're going to go a little bit more in depth with that whenever we look at our solids, though, and you'll kind of see why some covalent bonding is stronger than ionic bonding. But if it's something just like within water, that can be separated a little bit easier. We also have those ion dipole forces. Those tend to be a little bit stronger than hydrogen bonding. And then we have those dipole-induced dipole forces, which tend to be a little bit stronger than dispersion. Those tend to not come up as much whenever we're comparing one substance to another, however. And we kind of rank these based off of their forces. So where people did experiments, looked at how much energy it took to actually separate some of these different substances, depending on what it was, and based off of how much energy it took to break it apart, that's how they got these rankings. And we talked about the intermolecular forces affect the properties of those substances. So kind of going back, intermolecular forces affect the melting points and boiling points of substances. So generally, the stronger the forces there are, it's going to take more energy to break them apart. So they tend to have higher melting points and higher boiling points if they have higher intermolecular forces. So since it affects the melting point and boiling points, therefore it also affects the physical state of the substance at a given temperature. So these intermolecular forces are what determine if a substance is a gas, liquid, or solid at room temperature. These can also affect the conductivity of a substance. So with things that are covalent, a lot of times, if it is completely nonpolar, it is going to not conduct electricity. But something like water that's polar can also interact with ions, which could mean that it could conduct electricity. These also affect the chemical reactivity, and we'll look at this a little bit later this unit, of if particles do not interact with one another, they cannot react. But if there's similar forces where particles can interact, it can cause a chemical reaction overall. Based off of the structure, it can also affect the hardness or softness of a certain material. So something like a diamond, even though it's just covalent bonds, is going to be much stronger than something like graphite or your lead in your pencil that is also just covalent bonds. So a lot of times those intermolecular forces and the overall structure are going to affect kind of the strength of that material. This is where we're stopping for today, and it is going to go on and talk about solids and what type of solids form and what intermolecular forces are associated with those.